All right, thanks. I know a lot of you are expecting me to begin my talk by making fun of DNSSEC, but I think it's important to recognize that DNSSEC has been deployed on quite a few computers around the internet. I have on the, I have a screensaver, unfortunately. This is what I get for using a new Ubuntu installation. On the right side here, you see a script which downloads the SecSpider database. SecSpider is a database from the DNSSEC people advertising all the zones on the internet that use DNSSEC. Don't do this from the network here. It's more than a gigabyte of data for all the information they have about the DNSSEC domains on the internet. The awk there parses the database, goes, okay, anything that's green, green, green in all these files that it downloads, that's DNSSEC is enabled. And then X-5 ends up being the IP address of the server, which at the end here, the script removes repeated addresses, so it only prints each IP address once and then counts the number of lines in this. So this is a popularity measurement for DNSSEC. Of course, popularity is not everything, but it is something. There was a recent scan which was showing that more than 1 million IP addresses around the internet are running QML SMTP servers, and of course I'm happy about that. I mean, I'm also happy using it for myself, but I'm happy if other people find it useful too. For DNSSEC, okay, thank you for the 2 QML users in the audience. For DNSSEC, does anybody want to guess what the output of this script is? 23. Now that's kind of insulting to DNSSEC. Any more realistic guess? 42. I get the feeling nobody's actually going to guess the answer here. You could guess a big number thinking that DNSSEC has been around for a while, but it's actually quite a new project. It's under 18 years old, started in 1993, and its marketing department only started a couple years ago when Dan Kaminsky said, hey, there's a security problem in DNS, but we've fixed it. All you have to do is download some new software. Except, well, the fix doesn't quite work. Maybe some people had pointed out the problem in the fix before, but Dan did a great job of saying, hey, here's this problem in a way that people can understand and convincing people to actually install the fix. But again, the fix does not completely work. It has a really serious problem with it, which added a lot of attention to DNSSEC. DNSSEC says, hey, we're the complete solution to this kind of problem. We will secure DNS. Now, DNSSEC, I ran this script a year ago, middle of 2009, a year after the Kaminsky announcement, and it said there were 941 IP addresses worldwide running DNSSEC servers. And then I ran it a few days ago and came up with 2,536, which is actually significantly more than 941. You figure this is, well, more than a year, but more than doubling, so it's like doubling every year. So in 20 years, DNSSEC is going to run out of IPv4 addresses. This is actually, you figure 1,000 people have been convinced to install DNSSEC name servers because, hey, your typical administrator has 2 or 3 addresses of his DNS servers, so 2,500 IP addresses, that's, well, say 2.5 name servers on average, 1,000 people who've installed DNSSEC, and that actually is saying something. For those of you not familiar with DNSSEC, you can find all sorts of reports that say what DNSSEC does for you. They paint these nice pictures of DNSSEC being something that defends you. DNSSEC is a lock for the internet. It's something you can plug your Ethernet cable into and, well, there's a picture from an actual DNSSEC report. Except DNSSEC is not actually like this. DNSSEC doesn't quite work to do what this picture might suggest it does. DNSSEC defends you in actually a somewhat more active way. Actually, it doesn't defend you. It's really purely an attack tool. So here's DNSSEC. DNSSEC is, right now, the top, by far, the top distributed denial of service amplifier on the internet. So let's see how that works. Take the same SecSpider database, go through it again. Well, this is a slightly more complicated parsing script, which instead of just printing the X-5 for the IP address, also prints Z, which is extracted from it a name, a DNSSEC protected name, along with some random number, sort by the random numbers, so that when you talk to these servers in a moment, they'll be in some random order instead of hitting one server a whole lot. Print out the IP addresses and the names, and put them in a file called servers, and then talk to the servers. Say for each server, Okay, let's ask the server a question. Let's ask it for all the DNSSEC information. Dig's a standard tool for asking DNS queries. Sends one packet, plus ignore means don't worry about switching over to TCP if the server asks for it. Just look at what you get from one, UDP packet, waiting for 1 second for an answer, and then parse the result, message size received. $5 here ends up being the size of the UDP packet received by the DIG program from this DNSSEC server. Now, this est here is estimating the amplification factor, 22 plus the size of the UDP packet. That's some estimate for 22 bytes of overhead on the network, divided by what's the size of the query that we sent? Well, let's figure it's the name plus about 40 bytes. It's just some estimate. We'll see how valid that is in a moment. And then print out the estimated amplification factor, the IP address of the server, and the domain name, and put that in a file called amp. Okay, a little more processing. Let's take only the estimated amplification factors above 30, and then let's print out for each, put these amplification factors in decreasing order, and print out for each server what is the maximum amplification factor of any domain from that server. That goes into a file called maxamp. Now, head -1 maxamp. Let's look at the first line. Estimated amplification factor of 95 from this address, 156, 154, 102.26, if you ask it for DNSSEC information for .fi. The total number of lines in this file is maybe even more scary. That's 2,326. Most of the DNSSEC servers on the internet will give you amplification factors above 30. And, well, they range from 30 up to 95 for these 2,300 DNSSEC servers. So, is this actually true? Do we actually have, thanks to DNSSEC being installed, more than 2,000 servers around the internet, 2,000 IP addresses at least, each of which will respond to a UDP packet with a UDP packet that is 30 times bigger? Well, let's try it. So you take two machines. Please don't do this unless you, in fact, own both of the machines. Let's say one of them has address 1.2.3.4, the other one has address 5.6.7.8. Those are the only two IP addresses left on the internet that have not been allocated. And now you run a monitor on the receiver machine, which is 5.6.7.8, to see how much traffic it's going to get. And you run a monitor on 1.2.3.4 to see how much traffic it's actually sending out. And now on that sender machine, 1.2.3.4, you set up raw sockets and forge packets. No, just do it from the command line. Set up an alias for your Ethernet. You can't talk normally from the sender to the receiver now, but they're on different networks and probably aren't talking anyway. So you set up a 5.6.7.8 address and then use DIG's convenient return address option, -B, 5.6.7.8, and send out packets just like before, asking for DNSSEC information from each of these servers, one UDP packet trying for 1 second. Of course, the return address being a different machine, this is being done on 1.2.3.4, get your responses to 5.6.7.8. 1.2.3.4 will never see the responses, so the DIG is just going to time out after a second and then move on to the next domain. Well, I tried this with actual IP addresses of two machines, one of them in the US, typical university computer, and then the receiver machine in Europe, and sustained an amplification factor of 51 for some number of minutes. And I could have kept doing it forever. So what does this mean for distributed denial of service amplification, which is the main function of DNSSEC? If you're an attacker and you have 10 machines around the network, each of which has a 1 megabit per second connection to the internet, and you send a total of 10 megabits per second of DNSSEC queries from those machines, then you get your DNSSEC drones to send 500 megabits per second to whatever measuring machine you have on the other end. All right, let's scale up. You've got 200 machines, each of which has a 1 megabit per second connection. This is not your most serious botnet in the world. You've got just 200 megabits per second of outgoing traffic. They go through the DNSSEC drone pool. You get 10 gigabits per second, which will take down not quite every site on the internet, but pretty much any site on the internet you can take down in this way for a cost of 200 megabits per second of your bandwidth as an attacker. Now, I don't know exactly what the limit is. This would require doing separate measurements on each machine. You try asking each machine for a flood that's spread between several measurement machines and then go through the 2,000. You could figure out what the limit is. I wouldn't be surprised if each of these machines has, on average, a 20 megabit per second connection, and then, well, times 2,000 computers, something like 40 or 50 gigabits per second is probably the current DNSSEC drone pool firepower. If you are an attacker and you don't think that this is enough, all you have to do is tell people to install DNSSEC. Hey, doubling every year, let's make a 100 gigabit per second flood pool. All right, that's enough about DNSSEC. I actually wanted to talk about security. Our goals in security are confidentiality, integrity, and availability. What we do in cryptography in particular, we have the legitimate users, Alice and Bob. Alice is sending whatever kinds of messages to Bob, and Bob is sending messages back to Alice. And then there's the attacker, Eve. Now, when you hear Eve in cryptography, you're supposed to think of somebody really evil. We don't like Eve in cryptography. Eve is a double agent working for the Chinese military and the movie industry. Nobody likes Eve. So what is Eve trying to do? Well, it depends. Eve has three things that she's trying to do. The attacker is trying to acquire data sometimes. Maybe there's private data being sent through the network, like who knows what Alice is sending to Bob. Well, Eve wants to find out if it's private. And so that's violating confidentiality. Cryptography tries to protect this by scrambling the information so nobody can understand it. In particular, Eve cannot understand it, while Alice and Bob can. Integrity. Eve might be trying to change the data. And availability, Eve might be trying to do denial of service to stop the data from getting through. The difference between integrity and availability is that availability means that from Alice and Bob's perspective, availability means you're getting the right data. Whereas integrity means you're not getting the wrong data. So if you're not getting any data, then, well, it's a violation of availability. That's a denial of service attack. But it's not a violation of integrity, if you know that you're not getting your data through. Integrity, you've had something corrupted without knowing it. So that's the three things we're aiming for in cryptography, the fundamental security goals of cryptography. I've titled this slide Cryptographic Failure Patterns because I've noticed some ways that Internet protocol designers tend to screw up these goals. And I'd like to point out some of those ways. I think most of this list is very standard, but maybe you'll find it interesting. Failure pattern number one, what Internet protocol designers often do wrong when they're starting out, is they say, oh, my network is secure. I mean, nobody's listening to what my computer is sending on this network, this corporate network or university network. What's the chance that any of the other machines are controlled by an attacker or a hotel network, a cafe, conference network? Of course, nobody's listening to the network. And so you get ridiculously easy attacks as illustrated by Firesheep breaking into all sorts of sites that are relying on this rather primitive type of cryptography where you have cookies that might be secure if nobody's listening to the network, but they're trivially breakable as soon as somebody uses TCP dump. Now, failure pattern number two, okay, maybe the attacker is sniffing the network, but protocol designers think, oh, what's the chance that somebody forges a packet? Now, this particular kind of mistake, this failure pattern for cryptography has a long history, goes back to, for instance, TCP and DNS, thinking that you're authorized by your IP address or sequence number or an ID. And if you have the right numbers put into your packet, then you're allowed to send that packet through, otherwise your packet is rejected. This is supposed to be security. Well, people keep believing that this ridiculous kind of security is actually security. For instance, TCP crypt, latest proposal along these lines. When Othello, the game of Reversi, was introduced in the US, it was introduced with a slogan of a minute to learn, a lifetime to master. And of course, people made fun of it, like a minute to learn, a minute to master. And while TCP crypt, a minute to install, a minute to completely break. If TCP crypt is targeted by somebody who forges packets, then it's completely broken. TCP crypt, here's a quote from the documentation. They're distinguishing between passive attacks and active attacks. Passive attacks, you use TCP dump versus TCP crypt. You're sniffing the network. What do you get? TCP crypt is encrypting your data. Look at all this encrypted data versus the clear text you would get without TCP crypt running. Active attacks. This is an actual quote. I didn't make this up. Active attacks are much harder as they require listening and modifying network traffic. Now, I'd like to see a show of hands. How many people here know how to modify network traffic? Anybody? Wow, you've just broken TCP crypt and you haven't even installed it yet. Failure pattern number three. Well, sometimes people are putting more work into integrity and actually thinking, what can somebody do to forge packets? Let's actually protect against forgery. We've got some integrity. But they're so focused on this that they forget about the other aspects of security, like confidentiality and availability. And sometimes they actually reduce confidentiality and reduce availability. So in the pursuit of integrity, you get solutions like, oops, DNSSEC comes back. DNSSEC, they say we're not doing any confidentiality. Your queries are public. If you don't like everybody knowing which domain names you're looking up, well, you shouldn't be using DNS. And then beyond that, it actually compromises your privacy. acadmedpa.org.br. This is some medical academy in the state of Pará in Brazil. They aren't on the internet. They haven't set up their website yet. Maybe they're still deciding whether they actually want to register acadmedpa.com. When they registered acadmedpa.org.br with Brazil, I don't think they thought that that name would be published. I don't think the Brazil administrators realized that they would be publishing their names. They turned off zone transfers, which are the normal way for DNS to publish names. Most DNS administrators have turned off zone transfers. But Brazil, org.br, turned on DNSSEC. And DNSSEC has a bug which reveals all the domain names. This was supposed to be fixed by something called NSEC3. They're running NSEC3. acadmedpa.org.br and basically all the other names are in fact public. So DNSSEC reduces your privacy. It's not just that it's not even trying to help, it's that it actively reduces your confidentiality. Same for availability. You've got a solution like DNSSEC or SSH or HTTPS. Already you lose availability by these protocols starting out with so many packets that they send back and forth trying to retrieve their cryptographic information, set up a cryptographically secure connection. You've got a bunch of packets which the attacker can interrupt. If the attacker forges a packet at any part of that initial setup, then the connection dies. It's trivial TCP resets or lots of other ways to break TCP connections like SSH and HTTPS. That's made quantitatively easier by having a lot of extra packets to do all the cryptography. Same thing for DNSSEC. And then, of course, DNSSEC goes further and turns itself into an attack tool, which amplifies the attacker power further to do denial of service. Failure pattern number 4, third parties. There was a great talk a few hours ago on SSL. It was in room number 2. Where there's apparently 1,400 certificate authorities that your browser trusts if your browser is something obscure like Firefox or Internet Explorer. And, well, all these 1,400 authorities, at least 1,400 machines around the net with various security problems and various rules that you can use to fool them, all of those machines can fake HTTPS, can forge whatever certificates they want and convince your machine that you're talking to whatever you think you're talking to through HTTPS. Some people say that we should avoid this problem by switching from the HTTPS authorities to the DNS authorities. But I'm not sure that the DNS authorities are worth trusting either. It's not clear that these people running the roots and .com are the people that we want to have in control of our security. So that's failure pattern number 4, is having trusted third parties. Oh yeah, it's okay to trust these 1,000 certificate authorities. It's okay to trust the root of DNS or .com. Well, no, it's not actually okay. Failure pattern number 5. Okay, somebody's deploying whatever kind of cryptography and they protect something. Let's call it X. X is what's actually cryptographically protected. The problem is that X is often not what we want to protect. The goal of cryptography is to stop security problems for the communication from Alice to Bob. Alice and Bob are talking to each other. Now, is that communication actually what is being cryptographically protected? And it's amazing how often the answer is no. For instance, a lot of times X doesn't get to Bob. A lot of times there's Alice or Alice's computer and then some middleman and then Bob. And you might get cryptographic protection from Alice's computer to the middleman and no cryptographic protection at all from the middleman to Bob. And so an attacker just has to sit on this network, forge packets to Bob, and Bob believes anything. And the cryptography is non-functional. For instance, in DNSSEC, I'm sorry, it keeps coming back. DNSSEC is deployed to the extent it's deployed on the client side. It's not actually put into clients, what people call stub resolvers, because it's this huge thing that you could never put into clients. And you don't want to be running something huge like DNSSEC on, say, your phone, maybe not even on your laptop. So people just put it on a middle cache. And then the attacker just has to forge packets from the cache to the client, and the client has no idea that it's receiving fake data. Another example, suppose somebody does get from Alice all the way to Bob. It turns out that what they're cryptographically protecting a lot of times is not actually Alice's data. The most common way that I've seen this happen is when people are actually encrypting something as security theater. They don't actually want to go through all the hassle of encrypting Alice's data. They just want to deploy cryptography so they can say that they've deployed cryptography. For instance, 2009, .org becomes the first open top-level domain to sign their zone with DNSSEC. Significant milestone in our effort to bolster online security for the .org community. We are the first open generic top-level domain to successfully sign our zone with DNSSEC. To date, the .org zone is the largest domain registry to implement this needed security measure. Now, if I hear somebody saying that they're implementing some needed security, particularly cryptography, I figure they're actually encrypting or signing whatever protection they're doing. I figure they're actually applying it to the data that you think you're getting out of them. But let's actually try that out. A few days ago, I looked up wikipedia.org, and it's the same for basically every name. Here's what you get back from .org. There's a signed part and there is an unsigned part. Now, the unsigned part at the bottom here is actually Alice's data, or Bob's data, whichever one of them is Wikipedia. The wikipedia.org servers have these addresses. That's the information in DNS. That's what you figure cryptography would actually be applied to. But it's not. That statement that those are the servers, that is not signed. What is signed is a statement saying, yeah, we've installed DNSSEC. More precisely, what it says is, yeah, there might be names whose hashes are between HH91 something and HHEPR something, but we have not actually signed any of those names. Sincerely.org, stamp. Now, it's cryptographically secure, your knowledge that they haven't signed Wikipedia.org. If they have Wikipedia.org, you can check for yourself that the hash of Wikipedia.org is in this range. They're actually giving you an answer that applies somehow to Wikipedia.org, saying that they haven't. This is so stupid. All right, suppose that .org gets its act together and actually signs the Wikipedia data. And you get that data all the way to Bob's phone, and Bob's phone is verifying the data. Then you still have this problem that's not actually the complete communication from Alice to Bob. Sure, I'm publishing some information like my IP addresses, but that's a pretty minor part of the information I'm publishing. What I actually want to make available to people is web pages, or maybe what I want to make available privately is email messages or publicly. So you have X in DNSSEC being, say, a server address. And what Alice is actually sending to Bob is not a server address. What Alice is sending to Bob is a mail message or a web page. And those are not what X is. Now, Alice can, of course, protect her web pages by installing HTTPS. But if she's using HTTPS, what exactly is DNSSEC doing? I don't know the answer to this. There is an answer from the DNSSEC purists, people who say, oh, wait. Actually, there's a reason that DNSSEC is good and HTTPS is bad. Now, you might have the opposite feeling. I have the opposite feeling, that HTTPS is actually a whole lot better than DNSSEC. But what DNSSEC purists say is HTTPS is bad because HTTPS lets Alice's servers control Alice's web pages. And wow, that's not how security should work. What we need is a military-style security model where Alice goes into a back room with a secure offline machine where she generates signatures on her data, and then those signatures can go onto her untrusted servers, which then distribute them, and anybody can check that those are signatures from the secure machine. So we've got offline signing in DNSSEC. Except this still isn't the right X. What X is signing, the cryptographically protected information in DNSSEC, is still not Alice's web pages. Now, if Alice wants to protect her web pages with offline signing to protect against whatever intermediate servers might be redistributing those, she could use PGP. If she's not using PGP, what is DNSSEC doing for her? The server still controls the web pages. If she is using PGP, what is DNSSEC doing for her? I don't understand what attack is actually stopped by DNSSEC. I'm going to go on a little tangent because I think this DNSSEC pre-computing signatures, and wow, that's the maximum security you can get, military-style pre-computed signatures in a secure room. I think that that's gotten some good publicity, but it's actually got a lot of problems. I don't think that pre-computed signatures are fundamentally such a good idea. Here's 4 reasons why. First of all, if you pre-compute a signature, then you're unable to handle anything dynamic. Your answers that you're giving to somebody that are signed, those are in some database which is static. It's sitting there, you sign it, and then you hand it out. Now maybe you sign something else the next day, but you can't be instantly generating data. Now, DNSSEC purists say, hey, that's how the web should be. You've got answers should always be the same. DNS is designed to give you static data. It might slowly change, but it's not going to change quickly. You're not going to differentiate between moments in time and generate any answers that might depend on exactly what your current status is. Imagine the web being like this. Imagine that you actually had Alice's data being required to be static for security. You'd have no PHP. You'd have no fun. You'd have this black and white web that's as boring as cr.yp.to. Not what you want for the internet. All right, number 2 problem with pre-computed signatures is that you can't even have the questions varying. You have to pre-compute your tuples, your database of question, answer, and your questions can't change. So if, for instance, you ask DNSSEC about some random name it's never heard of, it does not have a pre-computed signature saying this name QPTIDSZL.DE doesn't exist. So instead it gives you back the kind of answer I showed you before, saying there's no DNSSEC names with hashes between this and that. Now this and that are hashes of names that actually do exist, and this hashing is what's supposed to protect those names from being revealed. But hey, you do 500,000 queries and you get under 500,000 queries. Some of the queries give you 2 new hashes that you haven't heard of. You do 457,000 queries at most and you get the 457,000 DNSSEC names in .de. And then you just invert the hashes. Now, some people will tell you that inverting hashes is hard. Cryptographic hashes, it's really hard to invert. That's true if you hash random data with a lot of entropy in it. But it's not true if you hash some human-generated string, like, say, vetamotors.de or akadmedpod.br or .org.br. To give you the scale of this, you can go through 1,700 billion names per day on a not very expensive computer with a couple of NVIDIA GTX 295 graphics cards. 1,700 billion names per day that you can guess against the hashes in, say, the .de database. After just doing 500,000 queries, so a few megabytes of data, and then you spend as much computer time as you want, and within a few days you got most of the .de names sitting on your computer. So this is problem number 2 with pre-computed signatures. Problem number 3, you need to store the signatures somewhere. If you've got your network, the internet over here, this is where Eve lives in cryptography, and you've got your interface to the network, and then you've got your database of data that your server is talking to, and then somewhere back here you've got the database generator, a person who's actually generating web pages. Then this person who's generating web pages could generate signatures, pre-computed signatures, that's the whole pre-computed military model, but where do the signatures go? They have to go somewhere in this database, and a lot of internet databases are not designed for that. Web servers are not designed for that. DNS servers are not designed for that. Mail is not designed for that. It's an incredible software upgrade problem to try to get signatures all the way through the system versus having cryptography just done once right at the edge of the network. I'll get back to that. And problem number 4 with pre-computed signatures is that they're fundamentally not fresh. If your data does change, an attacker takes the old data and then replays it whenever he wants. Hey, here's a valid signature, which he sniffed off the network, and then shows you the old valid data. It's still a valid signature. So now the attacker is taking any of your old answers and pretending that they're new answers. Now you could put time limits on your signatures. You can have expiration times on your signatures, assuming that everybody's got a reasonably synchronized clock. But then you get all these administrative problems with trying to re-sign your data. Suppose you don't want the attacker to be able to replay old data for more than a few days. Well, okay, let's have an expiration time of 2 days on your signatures. Every day you have to generate new signatures, and that a lot of times goes wrong. For instance, .us committed DNSSEC suicide a few months ago. .be committed DNSSEC suicide in October. All right. In some sense, I haven't said anything about cryptography so far, but I have a few more failure patterns that actually have something to do with cryptography. I think a lot of times failure pattern number 6 comes from people who see that something has been specified and standardized and then turn off their brains. Failure pattern number 6 is, hey, I have to choose some cryptographic mechanism. Well, here's something that a cryptographer wrote down and put into a standard, so it must be okay. but it's not okay. Something like the data encryption standard, 512-bit RSA, or MD5-based certificates. Hey, these were all standards, and they were used for years and years and years after no cryptographer would ever have endorsed them. For instance, MD5. You can find public statements in 1996 from top cryptographers saying, don't use MD5. And what does the internet do? It keeps using them. Internet protocol designers keep using MD5 till 2008, and well, maybe even a little bit still today. Failure pattern number 7. Oh, suppose we move up to 1024-bit RSA. A lot of people will tell you move up to 2048-bit, but suppose you say 1024-bit is enough, as DNSSEC tells you. 1024-bit RSA is enough. Well, that's breakable in 2 to the 80 operations. This 80 is some rounded thing. Maybe it's 2 to the 75, maybe it's 2 to the 85, but something like 2 to the 80. Oh my God, it's such a huge number. We'll never do 2 to the 80 computations. That's infeasible. Except it's not feasible. 2 to the 80, let's compare this to an attack going on right now, which is going to be done pretty soon, and it's going to have a total of 2 to the 77-bit operations. That's just an academic attack. To put this in perspective another way, if you have one GTX 295 graphics card, you can do 2 to the 69-bit operations per year. If you have a couple thousand of those, then that's 2 to the 80-bit operations per year. 2 to the 80 is not actually that big a number. Now, some people, failure pattern number 8, take more of an economic view. Protocol designers often say, oh yeah, even if somebody can do 2 to the 80 operations, well, they wouldn't be able to do 2 to the 80 operations for the amount of budget that they would apply to me. I mean, my data isn't worth having a few thousand graphics cards. Nobody would spend those kinds of resources. As a cryptographer, I'm extremely uncomfortable with that reasoning for a few different reasons. First of all, the attack costs that I just mentioned, like a couple thousand graphics cards, actually that's nowhere near the state of the art. If you have a Radeon 5970, which is not the latest card from AMD, then that's a few times faster than a GTX 295. Use FPGAs, you can gain even more. And of course, if you can build chips, as some attackers do, then you can get the attack going much, much, much faster. But it's even more scary. There's algorithms like batch NFS. NFS is the attack we use to factor RSA keys. Batch NFS attacks a bunch of RSA keys for less than the cost of one RSA key times the number of keys that you're attacking. So the batch amortizes the cost of your cryptanalytic computation across a bunch of keys. You can attack a bunch of keys for less cost than you would expect just looking at the cost of one key. And then third reason that this economic argument doesn't make sense to me, and that I really don't think it's a good idea to be cutting things this close, is that the attacker is often not paying any money at all. For instance, Conficker broke into, well, the maximum, it was estimated to have 12 million computers. Of course, after some eradication, it was down to only something like 7 million, and the controls seem to be somewhat cut at this point, but it's not that hard to break into a huge number of computers and get them to work doing your cryptanalytic computations for you. So as a cryptographer, I would never endorse a system at this kind of security level. We will see these systems very publicly broken in not very many years. Failure pattern number 9. This is so complicated, I don't understand it. Nobody who's attacking it could possibly understand it either, so nobody's ever going to break it. Nobody would ever be able to figure out this system. We've seen a lot of examples like this in HTTPS, but maybe people aren't so familiar with examples in DNSSEC. Like 2009, Bind announced they had a bug where you could forge DSA signatures trivially. Now, not so many people use DSA signatures. This is maybe hard to exploit, kind of like HTTPS renegotiation. But then there was the next bug, another bug in DNSSEC implementation where an attacker could forge any data. What does DNSSEC mean if you can just forge arbitrary data? 2010, oh, another bug. You end up with forging arbitrary data. Okay, that's probably the end of the list, right? Well, no, it's not the end of the list. If you've got 1 million lines of code that are supposed to be implementing your cryptography, you're not going to get those 1 million lines of code right. This is not the direction that we need for cryptography or for other aspects of security, but hey, if we can't even get cryptography right, we don't have any hope of any other kind of security. All right, failure pattern number 10. People say cryptography has benefits. And if it has benefits, oh yeah, of course people will install it, except it also has costs. And the most obvious cost is speed. There's also ease of use, but I don't have nearly enough time to talk about cryptographic ease of use issues. Google is a nice example of how cryptography is obviously too slow to be widely used. You can do a text search on Google now, HTTPS, google.com, and I've got two screenshots here which look very similar for Google through HTTP and through HTTPS. Got the same search results and the same spam on the right side, but you see some differences, like there's a picture here, a preview, which you only get if you're doing the unencrypted web. And then if you look more closely, you see a top line, which is only on the unencrypted version, saying images, maps, videos. You only get those unencrypted because Google doesn't have, even Google, with all its computers, they don't have enough computer power to encrypt all their images and maps. So if Google, as an example of a company that's surely better equipped to handle load than anybody else, if they can't afford to encrypt all their data, it's not a surprise that 99% of the web servers out there don't encrypt the vast bulk of their data. So HTTPS, hey, it actually works pretty well for the sites that manage to get it working and running and don't get overloaded by it. But for the vast majority of websites, it's inconceivable to actually use HTTPS. Now, I'm a cryptographer, which means I'm supposed to have been helping solve this kind of problem. But I look at the internet and it's embarrassingly insecure. The secure internet is this ridiculously small fraction of the entire internet. The only thing I can think of that's a smaller fraction of the internet is IPv6. This is really, really embarrassing. So at this point, I should be committing harakiri, but actually, I'd like to tell you what I've been working on, because I think there is hope of doing better. Taking HTTP, and without overloading sites, without making anything hard to use, adding some really high security. And not just security theater, like, oh yeah, we'll have something signed, or we'll have something that's breakable by anybody who sniffs and then forges packets. I think it's possible to actually have some real security. And I'm going to start this description in what might sound like a totally crazy way of don't think about speed at all. I should say that part of what I'm going to describe here is things that I've talked about before, like DNS curve, but today's the first time that I'm giving the big picture. This is what I'm trying to do for the whole internet. Now, again, this starting assumption saying that cryptography is instant, that we don't have to worry about the speed, this is how could you possibly assume something like that and imagine getting it deployed? I just said that, hey, we can't even deploy HTTPS on more than a small fraction of the web. But let's imagine that cryptography actually gets to this point, that it's just amazingly fast. Then how would we design a security system? How would we integrate security into the internet? Well, you can start thinking about this and actually come up with some pretty simple answers. First of all, what cryptography do you choose? Well, there's a pretty obvious choice. Right now, the best that you can get for key sizes, for confidence level in cryptography is elliptic curve cryptography, which has been around since 1985. If you take a strong 256-bit elliptic curve, that's something which in 1985 would have taken 2 to the 128 operations to break, and today takes 2 to the 128 operations to break. RSA, there were better and better attack algorithms in the early 80s, the early 90s. Elliptic curve cryptography, when it was introduced, said, okay, we're not going to have those problems for the following mathematical reasons, and it's been true. It's held up perfectly for 25 years. Now, I said 2 to the 128 operations. Right now, 2 to the 128 is comfortable. It's maybe not forever perfect security, but it's comfortable. It's going to take us quite a few years before 2 to the 128 is at all worrisome. And then I'm also going to assume that the attacker doesn't have a quantum computer. Now that's something I'm actually more worried about. And if you're also worried about making cryptographic solutions that resist quantum computers, you should look at pqcrypto.org for post-quantum cryptography. But for the moment, nobody's building a quantum computer. At least nobody's building a big quantum computer that would be useful against crypto systems. And it's going to be quite a few years before we have any trouble with this. Now, what do we do with this cryptography? What do we get out of cryptography? Well, the maximum security you get, the fundamental stuff that cryptography does for you is it takes a message and it completely protects it against espionage, against sabotage. It's taking your message and encrypting it and authenticating it using public keys. You don't have to meet in advance and share a secret key. You've got a public key for Alice. Only Alice knows her secret key. You've got a public key for Bob. Only Bob knows his secret key. And then Alice, using her secret key and Bob's public key, sends a message, encrypts it, and authenticates it to Bob. And then Bob uses his secret and Alice's public key. I'll get back to how they know their public keys. Bob uses Alice's public key to verify the message and uses a secret key and decrypts the message. And then he has the original message. Eve, the attacker, can't figure out what the message is, can do traffic analysis, and you have to still do things like Tor to protect yourself, but Eve can't figure out what the contents of the message are, and Eve can't forge a message that passes verification. Now, there's an improvement that you can make to this picture very easily. If you can encrypt and authenticate whatever length of message is, then you can certainly encrypt and authenticate packets, short messages. So let me make that little change from message to packet, message, packet. The reason for doing this is that suppose you have a long message, a megabyte long message, and you encrypt it and authenticate it. You could use something like PGP. And then you send that message through the network somehow. And then Bob verifies it and decrypts it. Well, the attacker can interrupt that megabyte anywhere, forge anything inside that megabyte, and then the verification fails. And now what does Bob do? Well, if you have verification on each packet, you split your long messages into separately verified packets, then maybe Eve isn't getting all of those packets. Okay, if Eve puts a lot of resources into it, enough resources, you can always deny service. But the question is, what's your amplification of the denial of service attack? Can Eve have just one little forgery interrupting a whole megabyte of communication? Or does Eve have to interrupt each packet? Well, if you split your long messages into separately verified packets, you get quite an increase in availability of your message in protecting yourself against denial of service attacks. Now, what do you do with these encrypted, authenticated packets? Again, this might sound totally crazy. I'm saying you're doing public key operations on every packet, every internet packet. You have public key encryption, signatures, whatever it is. So from a speed perspective, what I'm saying should sound totally insane. But imagine that it's not a cryptographic performance problem. Then, hey, we might as well just put every packet that we send into this protection, and then do we do that inside TCP, which is what SSH does? SSH does some protection on each packet and then sends it through a TCP connection. Same for SSL. Well, that's not a good solution because Eve can just interrupt the connection at any moment at the beginning, and it also takes a long time to set up the connection, exchanging cryptographic data. So you get much better availability and much better speed. You get a connection instantaneously set up if you just send UDP packets instead of TCP packets. Now, this might also sound crazy because, hey, UDP is the unreliable datagram protocol. So how do you get reliable communication from Alice to Bob? Well, that's a problem that's solved by TCP. TCP adds reliability on top of IP, and you can just do what TCP does on top of cryptographic protection on top of UDP. So CurveCP is a new protocol which is very much like TCP, but at every packet you've got cryptographic protection. Assuming that Alice knows Bob's public key, and assuming that Bob knows Alice's public key, well, actually, the server doesn't need to know the client's public key to set up a connection, but one side does need to know the other side's public key. This protocol, you can think of it like IPsec, except it's higher security than IPsec. It's fewer packets than IPsec. It's really just as fast as TCP, with a little extra cryptographic protection in each packet, which, again, might sound like an insane performance penalty, but let's imagine that that goes away. How do we take a protocol like HTTP, and how do we protect HTTP using CurveCP? Well, somehow Alice has to start retrieving a web page from Bob. Alice says, okay, I'm looking up whatever Bob's URL is. I've got that in Alice's browser, knows the URL. Alice is clicking on a link, and then how does the browser start setting up a secure connection to the server? Well, if you're going to have a public key protection on your connection to something, you need to know the public key that you're talking to. Alice needs to know Bob's public key. Where does Alice get Bob's public key? Well, actually, that's really easy if you make the system somewhat harder to use. This is a standard solution to third-party problems. If you don't trust the middle of the network and you're willing to suffer somewhat in setting up URLs, then you can put public keys into URLs. So these are called NIMs. This is a public key protected name for your server, is a key which is put into your URL. So you look at a URL, suppose that you were willing to tolerate clicking on a link that has a public key in it, which means you would have to put those into all your links and advertise those on your business cards. Definite usability issues. But suppose that you're willing to go to this extreme. You just have a key sitting inside your URL. 123867539. That's not quite as long as an actual key. Actual keys are 32 bytes, and then they get encoded as something like 50 bytes inside a URL. Everybody recognizes a magic number and a key, and then they instantly know the key. So wherever you got the URL from, whatever you were clicking on, if that includes a key, then hey, it's really easy to just extract that key and start making a secure connection. Alice knows Bob's public key and connects to Bob's server, and then Bob, along with that, sends her public key. Bob can send data back to Alice. Of course, this is not the most usable thing in the world. So let's look at the normal case, that the user just has something like twitter.com, www.twitter.com. That's a URL that you're looking up. How do you have security for that? Well, DNS already has aliases. They've got some reliability problems, but you can avoid those. CNAMEs or aliases inside DNS. All DNS software supports this. You can just take www.twitter.com as a Twitter administrator, Bob. You just set up this alias from www.twitter.com, CNAME, to your name. And there's a public key of your server. So Bob sets up his public key on his server and sets up this CNAME for www.twitter.com, and there's a public key that anybody can see. Now you might say, wait a minute, how do we get security for this distribution of public keys? I'll get back to that in a moment. There's another little technical problem with CNAMEs, which is, suppose you have twitter.com instead of www.twitter.com. Well, you're not allowed to use a CNAME and an NS at the same spot, so you have to have the information encoded in the NS instead of the CNAME, but this can still be done with no extra communication and with no extra work for Alice to look up Bob's key. All of the information here, all of the public key distribution is something that Alice gets as part of the current DNS protocol with no extra work. Alice just sees Bob's public key and now runs CurveCP instead of TCP to connect to Bob's web server. Just as fast as HTTP, but secure. From Bob's perspective, he doesn't want to change his web server. He doesn't want to have some new protocol that he has to wait for whatever web server he's using to support. So he just sets up a forwarder. There's a couple details that I'd like to emphasize here. The forwarder for CurveCP, first it's running over UDP, like I said, and it's running on port 53, not on port 80. Nowadays, it's pretty easy to get packets through to port 53. This is what minimizes the deployment effort for people. If you run something on port 53 and then forward it to whatever port it's supposed to be going to, then that's generally very easy to set up. So you just take your existing name service port, port 53, and then run on it a separate little utility, a forwarder, which talks to whatever servers you have running right now. Bob doesn't have to change his servers. He just installs a little forwarder and puts its key into DNS. How did Alice get this information of the twitter.com NS record or CNAME record? Well, Alice got that from a DNS server. This is what DNS Curve is doing. DNS Curve is the big picture I've described, but restricted to the case of DNS. In DNS, you're talking to a server. It's just like in HTTP, you're talking to a server. How do you find the public key of the server? Well, it's in the name of the server, which you get while you're looking up the server address. I already showed you the twitter.com NS having a public key inside it, 8675309. Alice, when she's looking up the name server address for twitter.com, is getting from the .com servers the twitter.com NS record, which Bob easily sets up without having to worry about how .com is handling its data. Bob just sets up inside .com an NS name for his site, twitter.com, which has a public key in it. He has a DNS Curve forwarder, which is receiving public key protected packets, forwards them to his existing DNS server, Everything's cryptographically protected over the network. All right. At the top of the tree, it's not quite clear who we should trust. If you ask, should we all be actually trusting the .com server, and then how do we get the .com keys? Well, the .com keys are something provided to you by the root DNS server. I used to think that this was a reasonable model, but I'm not so sure anymore. I don't think it's a good idea to have a single root key. I think lots of people are coming to the same conclusion. It's not even so clear that it's good to have a single .com key. You can protect yourself very easily if you're willing to use these NIM URLs, URLs that have public keys in them. Again, it's not so easily usable using that kind of URL. You can protect at least the integrity of your communication against .com misbehaving, against the roots misbehaving. You can't protect your availability, and .com can always interrupt communication if everybody's asking .com for where your address is. No matter what public key protection you try to add later, you can defend yourself against .com changing your site, but you can't defend yourself against .com taking your site offline. This is something where there's lots of proposals to deal with it. For instance, Telecomics DNS, BitTorrent DNS. I don't know what we're going to end up doing. I don't know who the authorities should be, how we should end up splitting the authority over names. But I do know that whatever the authorities are, whatever their keys are, this is a very easy way to secure the communication with them. So that's CurveCP. Now, the deployment costs of this, all Alice had to do was take her existing DNS and HTTP lookups and run them through some proxies. So her DNS cache, her DNS lookup agent, which is running on her machine, that takes her existing web browser DNS requests and forwards them through DNS Curve. And her HTTP client, her web browser again, her HTTP connections go through an HTTP proxy on her machine, which forwards everything through CurveCP, if it's talking to Bob's machine, which has installed CurveCP. On Bob's side, he also just installs a little forwarder and then sets up some DNS information. That's all Bob has to do. He doesn't have to change any of his DNS information, doesn't have to change his DNS database software. The middle of the internet doesn't have to change their database management software, which has been a major hassle for DNSSEC. Firewalls generally don't have to change. Sometimes you have to open up port 53, but usually people have it open already. They're running their own DNS servers. Don't have to change web browsers. The deployment costs are, as far as I can tell, minimized. The number of pieces of software that have to change, that's minimized. So this is, as far as I can tell, the easiest possible thing to deploy, assuming that the cryptography is free, assuming that the cryptographic computations are instantaneous. This gives every single packet cryptographic protection against espionage and sabotage, and to a large extent against not just corruption, not just giving us integrity, but also gives us availability. Dan Kaminsky says this is a disaster for DNS because, well, if you have a secure link from Alice's computer to Bob's DNS server, then you abandon caching. This is the exact quote. You abandon caching, you get 100 times increase in load for DNS. Plus, as I've been saying, it's crazy to imagine we can do public key cryptography so quickly. But let's look at this issue first. I have a few responses to Dan on this point. First of all, Bill Manning did measurements, and he came up with a slightly smaller increase than 100 times. In fact, he came up with an increase of 1.15, which is not exactly threatening the integrity of the internet. If you have a typical DNS server, you have so little DNS load, you wouldn't even be able to measure this. If you have a very busy DNS server, then you've already provisioned it for much more than 15% fluctuations in load. Actually, DNS server operators are worried about denial of service attacks, and they give themselves much, much more capacity than you could possibly generate from all the legitimate laptops and end computers in the universe. The big DNS server operators like VeriSign are setting up 200 gigabits per second of capacity because they're trying to resist serious distributed denial of service attacks. Now, you're not going to generate 200 gigabits per second from any number of legitimate computers working normally, no matter how little caching they do. The final point about abandoning caching. and how much of a disaster this would be for the internet, is this is blowing DNS completely out of perspective. When you're setting up a secure connection right now, you're doing HTTPS for kilobytes or sometimes megabytes of data after a few hundred bytes of DNS at the beginning. And even if that few hundred bytes of DNS is not cached, even if it isn't reduced to 0 bytes, it's just a few hundred bytes. It just doesn't matter. What matters is the communication cost of all the secure communication afterwards through HTTPS, and HTTPS, that's not the problem that we're having with HTTPS. The HTTPS is not overloading servers because of people not caching it. It's overloading servers because it's fundamentally really, really slow, tons of packets and tons of cryptographic operations. So finally, what about the cryptographic speed? I've said imagine that public key cryptography could be instantaneous, and the surprise is that it is. Public key cryptography is so fast that one typical few years old server can handle a 20 megabit per second connection without being overloaded. You have to use state-of-the-art cryptography for this. You have to use elliptic curve cryptography. Nothing else will give you this kind of speed. It's possible that hyperelliptic curve cryptography can, but what we have now that's giving this kind of speed is elliptic curve cryptography with very high security curves, all the security standards that have been developed over the past 25 years, plus a few new ones to make the implementation easier without violating security, for instance, without using lookups that are vulnerable to cache timing attacks. That's in this software that you can download right now, use from C or C++, very simple interface called CryptoBox, which takes your cryptographic packet and puts it in a box, protecting it against sabotage, against espionage. The code is validated much more extensively than any other cryptographic library out there. So you can download this library. Again, it's public domain, C or C++, Python coming very soon. There were some initial requests for Java support, but that's not so high on the to-do list. Finally, the speed. Here's the numbers. Again, this is fast enough that you can handle 10 million packets with different public keys in under 10 minutes on pretty much any CPU the last few years. That leaves the rest of the day free for handling whatever it is that you want to do with all of those 10 million clients you're talking to. It's just not a problem to handle this amount of CPU time. It's really, really fast. It's better than just handling 10 million packets per 10 minutes. It's 10 million new public keys in 10 minutes. And then if a public key gets reused because a client is doing a lot of packets back and forth for a long connection, which is very normal, then all of the public key work is actually shared between those packets. So you get very, very fast packet handling, and every new client is giving a very small amount of extra CPU time. Again, to do denial of service on this through CurveCP right now, you would have to have something like 20 megabits per second going to a single Core 2 quad. This is just, it's fast enough, so we can actually do a very simple, very easy to deploy, very high security system. My last slide is just a bunch of links. If you're interested in following up on some of the things that I've talked about, for post-quantum cryptography, thinking ahead to somebody builds a quantum computer, we want the internet to resist that. Of course, if we can't even resist current attack computers, then we're in trouble, but imagining that this works and we can actually stop all the current cryptanalytic attacks, we still have to worry about future post-quantum attacks, so go to pqcrypto.org. If you're interested in measuring the DNSSEC amplification and the privacy violations that I've described, find acadmedpa.org.br for yourself. I should mention Ruben Niederhagen's fast GPU software that I described, 1,700 billion names per day. That is not yet on this site, but I imagine that once he makes it even faster, then he'll decide it's done and it'll be up here. If you're interested in DNS Curve generally, go to dnscurve.org. Plus, very recently, Harm van Tilburg has released a complete DNS Curve forwarder. So go to curvedns.on2it.net, and then you can be running Curve DNS for DNS Curve support on your own name servers. And finally, if you're interested in CurveCP and very lightweight, high security protection for HTTP, go to the CurveCP mailing list. Just send email to curvecp-subscribe@list.cr.yp.to. Thanks for your attention.
So thank you very much for your talk. I think we still have some minutes left for questions. We have 2 microphones here. Please line up in a queue behind each of them, and we will get to your questions. First one, please.
Hi, thanks for the talk. Really good. I had 3 questions. I'm okay if we don't get to all of them right away. My first was, in response to Dan Kaminsky's work on tunneling over DNS, I've advised network operators to bandwidth throttle port 53 UDP. How do you think that's going to interact with this proposal?
Sorry, there's a bunch of echoes here. You said bandwidth?
Bandwidth throttling on port 53.
Yeah, sure. You can, of course, limit the amount of data that's coming into port 53, but at some point you have to accept that people are going to be sniffing your network and not just doing blind attacks. So then most of the solutions don't work.
I have a slightly different question, which is, how does the end user who's trying to use CurveCP on a network which has port 53 throttled down to, say, 1 kilobyte per second of throughput, that's going to affect the user's experience of using CurveCP as you described it?
Sure, there are certainly cases where the firewalls are set up in a way that you have to reconfigure in order to get port 53 working reasonably.
Thanks. Second question is, you've got CurveCP is a new implementation that's going to have to re-implement all of TCP's bandwidth sharing measures and fairness and so on. How do you anticipate that work going?
That work is done, so congestion control and so on is all completely implemented. Yeah, it's a very important part of TCP to handle retransmissions in a way that doesn't overload congested parts of the network, and that's actually something where it's surprisingly complicated, but it can be done and has been done. That code is completely done.
Okay,
Thanks.
one last question from the peace missions. So the question is, does you really believe that anyone is going to deploy this at all? And when did he publish this, and how many have adopted it?
I got the first part. There were too many echoes for the second part. The first part was, do I believe that anybody will deploy this at all? And, well, we'll see. It's something where if people like other solutions better, if other solutions work better, then great. But if this is the best thing out there, then, hey, there's a chance that it's going to be deployed.
So, thank you for your talk. I have to close the talk now.